Morning. As Deborah just mentioned, my name is Linden Wike. I'm a graduate student at the University of Maryland, and I will be talking to you today about using synthetic seismic methods to locate lava tubes and other void spaces with applications to the Moon, Mars, and other planetary bodies. So to start off, we've talked about lava tubes a bit in this section so far, but subsurface cavities are extended beyond just lava tubes, and they are cavities that can be filled with air, fluid, vacuum, and they are found to be in various dimensions and depths throughout Earth, Moon, Mars, and other terrestrial bodies. Seismology is one of the geophysical tools that we can utilize to detect and characterize these voids on each terrestrial body and can serve on Earth as an analog method for how we can make studies and go into the field on other planets to detect them there as well. Here I will be talking about benchmark models of seismic wave fields that can interact with these void spaces to provide an estimate for what seismic analysis we can expect from terrestrial data and other data that can sort of give us a first step in how we go about finding these features. This presentation will focus mostly on the seismic reflection method with future application of refraction and surface wave analysis. You can see in these images here, I have Skull Cave, which is another, alongside Valentine Cave, is a lava tube and Lava Beds National Monument. And on the bottom right here, we have the Marius Hills Hole, which is on the Moon and believed to be a skylight into a lunar lava tube. So to start off, I'll talk about my model space and my simulations. We have here a set of 9 different geometries of Skull Cave. We have a small geometry, which has about a 2.3 meter diameter, an original or medium geometry, which has a 23 meter diameter and is most closely related to what Skull Cave actually is, and a 46 meter diameter, which is double the size and on the larger end of what we can expect lava tubes to be on Earth. These tubes also have varied depths to the ceilings of the tubes of 6 meters, which is about where Skull Cave is right now, 25 meters and 50 meters. So these are 9 different geometries, and from seismic data, we can expect the larger tubes at greater depth to be the most easy to see because they will have the strongest signal. My meshes I create via an open software called Gmesh, and they propagate in a different open software called SpecFem 2D, which you can see in these GIFs on the right here. And you can also notice from these that there's a limitation in these simulations where I have wall reflections of these blue and red waves, which can interfere with the seismic data we expect from pure reflections off the top of these tubes. The receivers and station spacing I used mirror what we can expect in the field when we conduct data on Earth. I have an 80 meter line, which has 0.5 meter spacing between the stations and 10 meter spacing between sources from 10 meters to 80 meters all along the surface with the vertical 100 hertz sources traveling straight down towards these lava tubes. So here's a bit of pre-analysis data. This is essentially raw data from the simulations where we can look at simply the synthetic outputs. The P wave and S wave, which are the 2 main sort of reflection waves that we can expect in seismics, have been removed essentially, which has taken out some of the interference of the wall reflected waves, but it does lead to more synthetic noise later in the simulation, which you can see at about 0.15 seconds and beyond. However, you can see that there are hyperbolae, which are indicative of lava tube diffractions, and they become readily visible with depth. You can see that the larger tubes, with the big tubes on the leftmost of these 3 figures and the small tubes on the right, they are harder to distinguish at shallow levels. They kind of blend in together with a lot of reflections coming in a short time span. But as we get deeper, these are pretty strong. You can quite clearly see where we expect this lava tube at about 0.015 seconds, and the smaller tubes have lower amplitude reflections than the bigger tubes. So here's my first step. I do seismic migration, which is essentially one of the big steps we do in reflection, where you take this time data, these hyperbolae, and try and geometrically place them back to where you expect this structure at depth. Here we can see the migrations from left to right of the large lava tube, the original lava tube, and the small lava tube. We can expect a signal around the midsection, 45 meters, at about 0.008 seconds, given a 2-way travel time. And you can also see here, however, that much of the reflection information is lost due to a large number of wave reflections within this small period of time. There's the wall reflected waves, there's multiple reflections from the lava tube, as it's only at 6 meters depth, and it's harder to sort of make out what's happening here. But you can see that the 46 meter tube does act more like a horizontal layer with a flat migration The 23-meter tube has some flat migration, but more curvature and is more impacted by wall-reflected waves. Most notably at about 0.1 second, you can see a sort of cross that is from the wall-reflected waves. And the 2.3-meter tube has the most distortion from wall-reflected waves and a lot of scattering and surface wave attenuation, and is not very distinguishable in this set. Here we talk about the seismic reflection migration of the lava tubes that have their ceilings at 25 meters. It's pretty similar to the one we just looked at, but things have been shifted down in depth as it's deeper. It takes longer for the waves to arrive, and they're now more at about 0.03 seconds, so an order of magnitude higher. Again, the 46-meter tube acts more like a horizontal layer. We have a pretty flat migration, but there's some visible curvature now that it's at depth. The 25-meter tube still has some curvature from the migration, but it's still impacted by the wall-reflected waves. But finally, we can see some curvature and effects from the 2.3-meter tube now that it's deep enough for information to reach us and not be oversaturated by lava tube wave reflections. Finally, we have a little look at the migration and the seismic reflection data for the 50-meter depth tubes. Again, we have flat layer for the 46-meter diameter tube. You can see that it's further in depth now at about 0.06 seconds, a little bit above that. And it's quite flat, quite clear here compared to the previous studies. The 23-meter tube is also pretty clear here compared to before, now that it's deep enough that we can essentially separate it from the other data within the synthetics. But the 2.3-meter tube is no longer visible. It's a tiny dot essentially at 50 meters, and we can't really take it out from the wall-reflected scattering effects. So a little look into the broader impact and further study that I want to conduct on this research. Our takeaways can be that GMesh and SpecFem2D are capable of modeling and simulating complex geometries. Here, this is the LiDAR data taken of Skull Cave that is simulated and put into synthetic models. Seismic reflection is also an applicable method to find anomalous structures such as lava tubes, caves, and other void structures at depth. And these benchmark simulations can serve as a foundation for understanding large-scale void structure on Earth and other terrestrial bodies. However, there are current limitations to this work, the main one being wall-reflected waves kind of contaminating and not making the synthetic data as clear as we would like it to be, which can be resolved. And we would look forward to incorporating refraction and surface wave analysis to other big parts of seismic data into looking out, sort of rounding out our understanding of how to detect lava tubes and make it more full, find where one has shortcomings and replace it with another sort of method. And there's also the application of these models to other terrestrial lava tubes, such as La Corona tube in Lanzarote, which also has LiDAR data and can serve as one of the 30 or so meter larger lava tubes on Earth at depth that we can expect. Thank you for listening, and I will take questions at the end of the session.